So let's start this week's problems. So this week we'll mostly deal with psychrometrics and a mixture of air and moisture. So previous week we saw mixtures in general, how to calculate mole fractions and so on. We saw some process happening with a mixture of gases. So this week is you can say a part of it. You have mixtures, but here you are considering air. You're considering which is dry air, so you don't have any water vapor and water vapor, moisture vapor in the air. These mixtures of that, and you'll also see some process in the psychrometric. How to see in the psychrometric chart and the processes involving that. So we'll move on to that. So, okay. So on that, maybe I think I'll first clear up the previous week's one, and I okay. So the previous week, this equation, it's correct actually. I was getting confused with the notations. So usually we use m or molecular weight. Here the capital M is for mass. So mass by your this is mass fraction. So mass by total mass will be your mass fraction. So what this equation essentially says is the total mass is equal with you calculate with respect to nitrogen and with respect to oxygen. So your mass of nitrogen divided by your mass fraction gives you the total mass of the mixture. So similarly, the mass of oxygen by mass fraction of oxygen gives you the total mass of the mixture. So you are just equating that and you are writing that expression in terms of nitrogen and oxygen. So just wanted to clear that up before starting this week. So with that done, any doubts on that? Okay, so moving to this week, the first question is, for a typical sample of ambient air, for a typical sample of ambient air at 35 degrees Celsius and 75% relative humidity and standard atmospheric pressure of 1.013 bar, the saturation pressure of water vapor at 35 degrees Celsius is 0.056 bar. The amount of moisture in kg per kg of dry air will be approximately. So they have given a set of condition of the air. They are asking you to find out the amount of moisture which is present in the air. So they are saying at the air is at 35 degrees Celsius and it is at 75% relative humidity. And they are saying that vapor pressure of water vapor corresponding to 35 degrees Celsius is 0.056 bar. So what will be the amount of moisture? So what we know now, starting, we know the dry bulb temperature, which is at 35 degrees Celsius, and your relative humidity is 75%, and atmospheric pressure is given 1.013 atmosphere. So that is the total pressure, including the dry air and the water vapor. Then you know the saturation pressure at 35 degrees Celsius. So now we can calculate your relative humidity as your vapor pressure of water vapor divided by the saturation pressure. So from this you can find out, you know saturation pressure, so you can find out your vapor pressure. So your relative humidity is given as 75%, so this will be 0.75 is equals to your vapor pressure divided by your saturation pressure at 35 degrees Celsius is 0.056. So this gives you your vapor pressure corresponding to 35 degrees Celsius is 0.042 bar. So now we can find out relative humidity. Sorry, you can find out omega, specific humidity. It's not a relative humidity, it's specific humidity. Omega has 0.622 into PV by P minus PV. That is nothing but PV by P of air. And this 0.62 comes because of the molecular weights. So 0.62 into PV by P minus PV. So this becomes omega is you know the vapor pressure value, and you also know the total pressure. So we can find out the specific humidity here. So specific humidity will become 0.027 kg. So omega is nothing but your mass of vapor divided by mass of dry air. So omega is 0.027. So for 1 kg of dry air, it will contain 0.027 kgs or 27 grams. So the option here will be option B. Next question is, we have the ambient pressure, temperature and relative humidity of air at a location as given as 101 kilopascal, 300 Kelvin and 70% respectively. So same, you know pressure, you know temperature, you know relative humidity. The saturation pressure of water vapor at 300 Kelvin is 3.6 kilopascal. So again, same specific humidity, you have to find out specific humidity. So same similar procedure. So you know pressure, you know temperature, you know phi. So P sat is here is 3.6 kilopascal. So you use with relative humidity 0.7. You can substitute here and find out your vapor pressure. You can find out vapor pressure, and again substitute in the specific humidity formula, 0.622 into PV by total pressure minus vapor pressure of water vapor. So that will give you the specific humidity. So here if you see, the specific humidity is asked in grams per kg. So you should be careful here. So omega here is 0.0159, will be in kg per kg. So you have to multiply by 1000, which becomes 15.9 gram per kg of dry air. So next question is, in a dew point apparatus, a metal beaker is cooled by gradually adding ice water to the water initially at room temperature. So the moisture from the room air begins to condense on the beaker when its temperature is 12.8 degrees Celsius. If the room temperature is 21 degrees Celsius and the barometric pressure is 1.01325 bar, find the partial pressure of water vapor in the room air and parts by mass of water vapor in the room air. So what it essentially is, you have a metal beaker. It's just like your normal ice water. You keep it in glass, you pour, you have condensation outside, you have water droplets outside. So a similar example. So what you have is a metal beaker and it has some water. So you are pouring ice water to this. Then what happens is the moisture in the air is starting to condense, and when the temperature is 12.8 degrees Celsius. So this gives you a dew point. And next they are saying that room temperature is 21 degrees Celsius, and they are also given your pressure, that is 1 atmosphere. So you need to find out the partial pressure of water vapor and your mass specific humidity. So we'll see how to solve this. So partial pressure of water vapor at dew point temperature of 12.98 degrees Celsius is 1.479 kilonewton per meter square. So partial pressure of dry air will be correspondingly, we are writing in terms of Newton here. So partial pressure of air will be 99.846 kilonewton per meter square. So we know water vapor pressure and your air pressure, dry air pressure. So using specific humidity, which is mass of water vapor divided by mass of dry air, this will come out to be 0.622 PV by PA. So we know both the values. On substituting, we'll find out that specific humidity is 0.009214. This is kg by kg of dry air. So now we need to find out what amount of water is present in the total quantity of air. So mass of water vapor divided by the total mass. So if you see, mass is mv plus ma. So just rearranging using omega value, you will find out that mv by total mass is omega by 1 plus omega. So substituting that, we will find out this is equal to 0.00913 kg by kg of mixture. So here we have taken 12.8 degrees Celsius because the water is condensing there, and it's some amount of water is removed from the air. So you have to consider that point. So what will be the corresponding air's temperature, because what is near this beaker, it will be at saturated condition. So moving on to the next question. Calculate humidity ratio, dew point temperature, density and enthalpy of atmospheric air when the dry bulb temperature is 35 degrees Celsius, wet bulb temperature is 23 degrees Celsius, and the barometer reads 750 mm of Hg with relative humidity of 36%. So we'll see how to solve this. So relative humidity is nothing but PV by P saturation, which we saw. So pressure, water vapor pressure currently divided by the saturation pressure corresponding to the same temperature. So now you know from the Bible 2035. Okay, so you can find out saturation pressure corresponding to 35 degrees Celsius, and you will get 42.2, and your relative humidity is given as 36%. From that you can find out your vapor pressure PV, which will be equal to 15.18. Next is to find out the specific humidity ratio. So specific humidity is 0.622 into PV by P minus PV, which is all. So we know PV, which I calculated, and P is given as 750 mm of Hg. You can convert that into Pascal or bar, whichever is convenient. Here we have written everything in mm of Hg. So you have to just add 13.6 into 1000 into G into H. So that will give you conversion to pressure in Newton. So here we have 0.622 into we are substituting because this is in ratio, so units will get cancelled out. So this is so we can directly substitute in mm of Hg. So 15.18 divided by 750 minus 15.18. So that is will be the pressure of air, dry air. So this will give you 0.01285 kg of water vapor divided by kg of dry air. So next is to find out the dew point temperature. So so dew point temperature is that point where the PV is your saturation pressure. So at that your pressure water vapor is saturation pressure, so it will start condensing. So that is your dew point. You will start seeing dews. So your temperature corresponding to PV will be your dew point temperature. So here your water vapor pressure, which you have calculated, is 15.18 mm of Hg. So corresponding to that, from your steam table you can find out that your temperature, saturation temperature, is 17.7 degrees Celsius, which is your dew point temperature. Next is to find out the densities. To find out density, we'll assume we can safely assume this mixture as follows an ideal gas equation. So we can substitute an ideal gas equation. So PV equals to nRT, or PV equal to mRT. So R will be your gas constant. So V by M, or you can write P equals to M by V RT. So M by V is your density. So you can write P equals to rho RT. So density is equals to pressure divided by gas constant into temperature. So for initially for air now, so we can find out the partial pressure of air. So partial pressure is your total pressure 750 minus 15.8 18 into, so multiply by 133.5. So that will give converting into Newton per meter square. So divide by RA is 287.1 for air, into your temperature is 35 degrees Celsius, so 273 plus 35. So this will give you a density of air as 1.1086 kg per meter cube. Next is to find out the water vapor density. So for water vapor density, similarly, so you have calculated the partial pressure of water vapor. So PV divided by RV by P. So pressure is 15.18 into 133.5. Your gas constant is 461, and your temperature is 273 plus 35. It will give you 0.0143 kg per meter cube. So density is actually you have to write 1 by rho equals 1 by rho a plus 1 by rho b. You have to calculate, you have to write total mass and divide by the total this thing, but here you can add straight, you have to add multiply with x. So we don't know that, you have to find total, first total mass divide by uh, the total density. So you have to find the total R first. So rho of the total density of moist air will be your total pressure divided by your RA plus RV, equivalent gas constant into temperature. So that will give you the total density. So you cannot straight away add density. So there's a mistake here. Then enthalpy is your Cp into temperature. So you see, if you take 0 as your datum, your air you are heating to some temperature. So Cp, the temperature difference, and omega is your amount of water vapor present in 1 kg of dry air. So that into your latent heat of water vapor plus your Cp of water vapor into temperature. So that will give you your enthalpy at that point. So assuming your 0 is your datum line, so this will what you get. So 1.005 is Cp of air, so Cp into T plus omega into your latent heat at 0 degree Celsius plus your water vapor temperature into T. So substituting your temperature here and specific humidity or humidity ratio which you have found out, substituting there, we can find out the enthalpy at that point is 68.15 kilojoule per kg of dry air. Any doubts in this? Okay. The next is cooling and humidification of moist air. So moist air at standard atmospheric pressure is passed over a cooling coil. Show the process on a psychrometric chart. Determine the amount of heat and moisture removed per kg of dry air. The inlet and exit states are as follows. So what is happening is you have a moist air at 1 atmosphere. It is passing over the cooling coil, and because of that you are removing some heat and moisture from the air. So the inlet and exit conditions are given. So inlet is at 30 degree dry bulb temperature and relative humidity of 50%. The exit dry bulb temperature is 15 and has a relative humidity of 80. So we need to find out the amount of moisture which has been removed and the amount of heat which has been removed. So if you see, this is how the process is. You have a cooling coil and there is air coming in at 1, which is 25 degrees Celsius and 50% relative humidity, and when it goes, the water in the air will get condensed on the cooling coil. So and you are taking that out, so that moisture is at 8 degrees Celsius, and then air which is coming out, this is at 15 degrees Celsius and 90% relative humidity. So if you see in the psychrometric chart, your bottom axis, which will give you the dry bulb temperature, and your wet bulb temperature will be a crossed lines. The diagonal lines will be wet bulb temperatures, and this curved lines which is shown, that will give you a constant relative humidity lines. And your on y-axis on the right hand side, so you will have your specific humidity or humidity ratio. So and you also have enthalpy lines which will be somewhat similar to your wet bulb temperature lines. So here now we know 2 points. So you know temperature, dry bulb temperature, and you also know humidity. So here is 30 degrees Celsius, not 25 degrees. So 30 degrees Celsius and 50% relative humidity. So that will be your state 1. Then second state is 15 degrees Celsius and 90% relative humidity. So that will be your state 2. So if we join these two state, that is your process which is happening. And then if you extend that to 100%, so that is will be your dew point temperature. So now we will see how to solve this. First, consider air around the cooling coil as a control volume. So when you apply mass balance, so your mass of dry air will remain same, because that is air is not getting condensed, only the water vapor is getting condensed. So air will remain same. So m dot A1 is inlet, m dot A2 is equals to m dot A. Now the amount of water vapor which has condensed and is coming out is m dot W3, which is given as your mass of dry air into the change in the humidity ratio, omega 1 minus omega 2. Now when you apply a steady flow energy equation across the cooling coil, so here, so your air is coming in at m dot AH1, and you have cooling heat which has been removed, Q, is equals to m dot AH2, which is going out, plus mass of water which is going out. M dot W3 into HW3 is the mass of water which has condensed and is leaving. So this is what. So we are having cooling capacity Q. So Q, amount of heat we are removing. So Q equals your exit minus inlet. So exit is your exit air and the condensed water minus the inlet air. So that's what we have written. So when you divide it the whole equation with respect to mass of dry air, which will come out to be Q plus H1 equals H2 plus omega 1 minus omega 2 into HW3. So now H1 and H2 can also be written in terms of dry air and your water vapor, because this is a mixture of air and water vapor. So we are writing in terms of dry air HA1 plus omega 1 HV1 equals HA2 plus omega 2 HV2, and similarly the condensed water. So so now we need to find out the specific humidities. So for that we know the pressures. We can find out the pressures corresponding to 25 degree Celsius and 15 degree Celsius. Sorry, 30 degree Celsius and 15 degree Celsius. So saturation pressure corresponding to 30 degree Celsius is 4.246 kilopascal, and 15 degree Celsius is 1.7051 kilopascal. And we know the relative humidity at inlet and exit. So from there we can find out your water vapor pressure. So your inlet water vapor pressure is 2.123 kilopascal, and I exit, similarly your relative humidity into saturation pressure gives you 1.3641 kilopascal. So now you know the water vapor pressure, partial pressure of water vapors in air at inlet and exit. So using that we can find out, the total pressure, so we can find out the specific humidities. So omega 1 is similarly 0.622 PV1 by PA1. So substituting that values at inlet, we will get your specific humidity as 0.01331 and omega 2 as 0.00849. So if you see, your specific humidity has gone down. So this says that there is some amount of water which has been removed, because omega is nothing but your mass of water vapor in air divided by your mass of dry air. So this gives you per kg of dry air. So this says that at omega 1, for 1 kg of dry air you have 13.31 grams of water vapor, and at state 2 you have 8.5 grams of water vapor for 1 kg of dry air. So that difference is the amount of water vapor which has been removed for 1 kg of dry air. So now we can find out the enthalpies of water and water vapor. So enthalpy of water vapor at 30 degrees Celsius. So here at HV1 is your water vapor, because it's in gaseous phase, and HW3 is your in liquid phase. So you have to use your liquid and gas enthalpies. So HV1 at 30 degrees Celsius is 2556.3, and similarly for 15 degrees Celsius is 2528.9, and at 15 degrees Celsius your liquid enthalpy of water is 63. So now you can substitute this in the energy equation to find out Q, amount of heat which has been removed. So HA2 and HA1 can be calculated using Cp delta T. So you know Cp of air is 1.005 and delta T is 15 minus 30, and substituting the omega values we'll find that Q is minus 27.3 kilojoule per kg of dry air. So you're removing 27.3 kilojoules of energy for 1 kg of dry air, and close to 4.8 grams of water per kg of dry air is condensed. Any doubts in this? What we did is we did in first mass balance across the cooling coil. So what is coming in, what is going out, we know mass. So we did it in two parts, one for dry air, it's the first equation, and one for your water. Next what we did is we did an energy balance across the cooling coil. So and we found out enthalpy, and we wrote enthalpy in terms of individual components for water and for dry air, and we found out the specific humidities for with the given conditions. So you know dry bulb temperature and your relative humidity. So using that we found out specific humidity, and using that and substituting the enthalpy values we have found out total amount of heat which is the cooling coil is providing. This problem can also be easily solved using your psychometric chart. So if you see, if you if you have a psychometric chart, if you see this 2 points, enthalpy can be directly calculated. So you will have enthalpy lines passing through those. So corresponding enthalpy lines you can take, and the difference between the enthalpy lines it will give you the Q directly. For H1 and H2, and you have to substitute for HW3, and specific humidity you will get it from the y-axis on the right hand side. So corresponding omega values you can take from, and you can directly substitute. Here we have calculated this humidities and the enthalpy of the mixed air. So moving on, the next question is, a stream of moist air at 2 degrees Celsius dry bulb and 80% relative humidity mixes with another stream of moist air at 30 degrees dry bulb and 10 degrees dew point. The ratio by mass of one part of the first to 2 parts of the second. So it's a mixing problem. So you have two streams of air mixing. So they are saying a stream of moist air at 2 degrees dry bulb temperature and 80 degree relative humidity. This is mixing with another moist air which is at 30 degrees Celsius and 10 degrees Celsius dew point. It is mixing in the ratio of 1 part of first to 2 parts of second. So 1:3 and 2:3. So calculate the temperature and specific humidity of the air after mixing. So we'll first calculate the properties of the first stream. So for the first stream, your specific humidity will be 0.035 kg per of water vapor for kg per dry air. So similar we can calculate what we calculated in the previous problems. So you can take the saturation pressure at 2 degrees Celsius. You know your relative humidity, so you can find out PV, and using PV and for 1 atmosphere you can find out your specific humidity. And similarly enthalpy, or you can straight away take these values from the psychrometric chart or any online psychrometric property reader. You can use that. So next is to find out mass of dry air per unit mass of moist air. So mass of dry air equals 1 by 1 plus omega 1 . So this equals 1 by 1.0035, is equals to 0.9955 kg. So if you have 1 kg of moist air, so what is the amount of dry air in that? So that's we have calculated 0.9955 kg. So for the second stream, similarly, you can straight away take it from the psychrometric chart. Your specific humidity is 0.00765 and your enthalpy is 49.67 kilojoule per kg of dry air. So now mass of dry air per 2 unit mass of moist air is, so this is twice of the previous one. So you are taking twice of 2 times of the dry air. So 2 into 1 plus omega 2. So this gives you 1.9848 kg. So if you have mixture, so you are mixing 0.9955 kg of dry air with 2 times of the second dry air. So 1.9848 kgs of second stream. So your equivalent enthalpy is a mass of the first into your enthalpy plus mass of second into enthalpy divided by the total mass. So this gives you the mixture enthalpy as 36.68 kilojoule per kg of dry air. Similarly, your specific humidity is your mass of water vapor in first into mass of water vapor in second divided by the total mass. So 0.9965 into your specific humidity plus second stream mass of dry air into specific humidity divided by the total dry air mass. So this gives you 0.00627 kg of water vapor per kg of dry air. So now using these two values from the psychrometric chart, you can easily find out any other property which you will need. So next question is, you have 1 kg of air at 25 degrees Celsius and 1 atmosphere and 70% relative humidity. They are saying it is compressed to 5 atmosphere in a polytropic process, given as PV raised to power 1.25. This is equals to constant. So that is a process in which you are compressing the 1 kg of air, 1 kg of moist air. It is then cooled to at constant volume to 25 degrees Celsius. So determine the humidity ratio and relative humidity of the air after the compression process. Also determine the amount of water that condenses in the tank and the final pressure. So we'll see how to solve this. So first we'll find out what was the initial properties. So initially the air is at 25 degrees Celsius, 1 atmosphere and 70% relative humidity. So your initial vapor pressure can be calculated as your relative humidity into your saturation pressure at 25 degrees Celsius. From your steam table you can find out your saturation pressure for 25 degrees Celsius is 3.169 kilopascal. So that into your relative humidity is given as 70%, so 0.7. So this will give you 2.2183 kilopascal. So now using, we know your vapor pressure, now we can find out your dry air pressure, partial pressure of dry air. Then using your specific humidity relation 0.622 equals your vapor pressure of water divided by your pressure of dry air. So substituting that values, so 1 atmosphere is 101.325 kilopascal. So and vapor pressure of is 2.2183. So substituting that will give me the specific humidity as 0.0139 kg of water vapor for per kg of dry air. Next is we need to find out what is the temperature at the end of compression. So this can be calculated, say because this is given us the compression happens as a polytropic process. So you can, for any polytropic process, it can write it as P2 by P1 equals P2 by P1 raised to power n minus 1 by n. So we know n is 1.25 because polytropic process PV raised to power 1.25 equals constant. So we know n. So we can find out your temperature at the end of compression. So P2 is P1 into your pressure ratio into n minus 1 by n. Pressure ratio we can know, it is 5 atmosphere divided by 1 atmosphere. So your pressure ratio is 5. Initial temperature is 25. So 273 plus 25. So this gives you your temperature at the end of compression is 411 Kelvin. So now after the compression, so because there is no water which has been added, your specific humidity will be equal. So omega 2 is equals to omega 1. So now using the above equation with respect to specific humidity, we can find out your pressure vapor pressure at state 2. So vapor pressure at state 2 is omega 2 into your total pressure at state 2 divided by 0.622 plus omega 2. So when you substitute your specific humidity value and your total pressure as 5 atmosphere, you will get your vapor pressure at state 2 as 11.07 kilopascal. So when you substitute this in your relative humidity equation, your relative humidity is your vapor pressure divided by your saturation pressure. So your temperature is 130 degrees Celsius, which is 411 Kelvin. So corresponding to that, your pressure is 341.92 and your vapor pressure of water at 2 is 11.07. So your relative humidity is 3.24%. So what happens is, this is the process if you see in the TV diagram. So 1 to 2 you are compressing, and then there's a cooling which is happening at constant volume. So this is just like any compressor where you are storing air in a reservoir. So initially you have a compressor which will take in air from the atmosphere, compress it and put it in a tank and leave it. So this tank will is at fixed volume. So that will cool the air which is inside, which is at higher temperature coming from the compressor. So this will release the heat to the ambient and it will get cool. So this kind of compressor and tank, they will always have a drain at the bottom, because you will have some water which is getting condensed. So to remove that, so this problem is a process which you can encounter in a daily basis. So your 1 to 2 which we have compressed, the compression process which I have already done. So initially it was at 25, now it has reached 138, and your relative humidity we saw has gone down, but your specific humidity is same. So relative humidity just says that how much more of water vapor it can take to become saturated. So that's what relative humidity says. So when at higher temperature, your air can take more amount of water. So that's why your relative humidity, when your temperature increased, your relative humidity went down. So this says that you can take a large quantity of water vapor at higher temperature. So now what happens is, now although the amount of water vapor has remained the same, the relative humidity decreases as a result of the compression process. Now since the cooling takes place at constant volume, condensation will happen, and when the specific volume of the vapor becomes equal to the specific volume of the saturated vapor, So if you see from 1 to 2 you had compression process, then this is in a TV plane. So 2 to 3 is a straight line, your constant volume process. So your specific volume at state 2, when it reaches that specific volume is equal to your saturation specific volume, that corresponding to that temperature it will start condensing. So we will assume your specific volume at state 2. So this being an ideal gas, we can assume. So RV T2 by PV2. So RV is 8.314 divided by 18 to find out gas constant, into 411 divided by 11.07. 411 is the temperature, and your pressure, water vapor pressure at the end of compression is 11.07. So 11.07 into 10 power 3. So this will give you 8.314 divided by molecular weight. So this will give you the gas constant into your temperature divided by the partial pressure of water. So that will give you your specific volume at state 2 as 17.15 meter cube per kg. So now if you see in the table, the temperature corresponding to at which you have your gas saturated vapor specific volume as 17.15, you will see your temperature is 42.8 degrees Celsius. So when your temperature is 42.8 degrees Celsius, your ambient heat is 25, so it can still cool. So if it cools down, then water will condense, because at this point your 42.8 degrees Celsius, your air is saturated, so it will come down, it will start removing water and will condense. So condensation thus will happen at 42.8. When the air is finally cooled to 25 degrees Celsius, air is still saturated, it will be in saturated state, and the final state of the water is a mixture. So at 3, your specific volume will remain same. So at corresponding to 25 degrees Celsius, you can find out your liquid and gas specific volumes. On substituting, you can find out the fraction of dryness fraction. So that will come out to be 0.3955. So from this we can find out what is the amount of water which has been removed. So a mass of water which has been removed is 1 minus x into your mass of vapor. So mass of vapor at state 1 is omega 1 into mass of dry air. So this is we know x, we know omega 1, which we already calculated. So on substituting, we will get 8.287 grams. So this is the amount of water which has condensed by compressing and then cooling. So now next is and we also need to find out the final pressure. So to find out final pressure, your pressure being a constant volume process, so we know the n temperatures, so P by T will be constant. So PA3 by T3 equals PA2 by T2. So we can write PA3 as PA2 into T3 by T2. PA3 is nothing but P2 minus your vapor pressure of water. So we know PV2, which is 11.07, and we know P2, which is 5 atmosphere. So substituting that, and T3 is known 25 degrees Celsius, T2 is 411 Kelvin. So substituting all the values, we'll get dry air pressure at state 3 as 359.308 kilopascal. So at state 3, we can find out the saturation pressure of water vapor at state 3 which is 25 degrees Celsius, is 3.169. So that plus 359.3 will give you 362.477 kilopascal. So this is the final pressure which will be there in the inside the cylinder. So any questions on this problem? I'll just revise it once. So we found out initial properties, and then we found out this goes in a compression is polytropic. So we found out what is the end temperature. Using that, we found out corresponding. We said that specific humidity or humidity ratio will remain same because there is no water which has been removed in the compression process. So correspondingly, what will be the vapor pressure? So we found out that, and then using that we found out what is the relative humidity. Then after finding relative humidity, we said there is a constant volume cooling, so we'll find out what is the specific volume. So we found out specific volume 17.15, and we saw that 17.15 correspondingly the gaseous saturated vapor specific volume corresponding to 17.15 was 42.8 degrees Celsius. So since this temperature was higher and the gas can be cooled further, air can be cooled furthermore to 25 degrees Celsius, we said that it will condense. So correspondingly found out what fraction is getting condensed. So 0.3955. So using this we found out what is the mass of water which has condensed. So using that we found out that mass is 8.28 grams, and then we found out what we need to find out what is the final pressure. So we said it is a constant volume process, so P by T is constant. So we know water vapor pressure at both the points. So at state 2 we know the temperatures, so we can find out the dry air pressure at state 3. So using finding dry air state pressure at state 3, and at state 3 water water vapor is saturated because constant volume process it's condensed, and your water is saturated liquid and saturated vapor is present. So the saturated vapor pressure is known, so the summation of those will give you the total pressure at state 3. So moving to the next question. So ambient air is at 5 degrees Celsius, 1 atmosphere pressure and 85% relative humidity is to be heated as it flows steadily in a duct, so that the relative humidity becomes 25%. If the volume rate is 100 meter cube per minute at the inlet, determine the rate of heat addition. Assume that the pressure remains constant. So ambient air is at 5 degrees Celsius and pressure of 1 atmosphere and 85% relative humidity. You are heating that as it flows steadily in a duct. So and at the exit your relative humidity is 25%. It is given that your volume flow rate is 100 meter cube per minute. You need to find out the rate of heat addition, and you can assume that pressure is constant. So we'll see how to solve this. So similarly we know dry bulb temperature and relative humidity, so we can find out your partial pressure of water vapor. So this relative humidity into saturation pressure at 5 degrees Celsius. So this gives you 0.85 is your relative humidity, so this gives you 0.74205 kilopascal. So that is your partial pressure of water vapor at inlet. So using this and your total pressure as 1 atmosphere, so we can find out the specific humidity at inlet. So 0.622 into vapor pressure divided by your total pressure minus vapor pressure. So this gives you a specific humidity as 4.59 into 10 power minus 3. Now at the outlet also the pressure is same as the inlet, because there is assumption saying that there is a constant pressure. So PV2 equals PV1, and your specific humidity is also same because you are just adding heat, and uh, because there is no addition of water vapor, your specific humidity will also remain same. So your P saturation at state 2 is equals PV2 divided by your relative humidity. So this gives you your saturated temperature at state 2 as 2.9682 kilopascal. So phi 2 is given as 0.25, 25% at except. So corresponding to this pressure 2.9682 kilopascal, if you see your temperature is 24 degrees Celsius. So now we know the exit temperature. So when you apply an energy balance across the duct, so there is no work transfer. So Q is Q plus in dot H1 minus H2. So in minus out is equal 0. So Q is mass of air. Your enthalpy can be written in terms for air and the water vapor. So m dot A Ha2 minus Ha1 plus mass of water vapor into enthalpy of water vapor minus enthalpy of water vapor at inlet. So again your dry air can be written as Cp delta T and plus omega if you divide it by mass of dry air into your the way water vapor is in gaseous phase, so Hg into at state temperature T2 and at inlet T1. So mass of air can be found out using the volume flow rate. So we have to find out the specific volume. So specific volume you will use an ideal gas equation. So P is rho RT. So 1 by rho is specific humidity. So specific volume. So RT by P. So RA T 1 by PA1. So we know we have found out in the previous what is the vapor pressure at 25 degrees 5 degrees Celsius inlet. So and we know the inlet air is at 1 atmosphere and RA is 278. Sorry, temperature is 278, 273 plus 5 and RA is 8.314 kilojoule per kg Kelvin and divide by your molecular weight. So this will give you a mass of air, dry air, so it is 126.072 kg per minute. So from steam table you can find out your enthalpy corresponding to 1 atmosphere and 5 degrees Celsius is 2509.7 and for 24 degrees Celsius is 2544.5 and temperatures T1 is 5 and T2 we have found out as 24 degrees Celsius and Cp of air is 1.005 kilojoule per kg Kelvin. So mass of air we have found out. So on substituting that, we can find out what is the amount of heat which has to be supplied to increase that relative humidity to 25 degrees Celsius. So Q is will come out to be 40.458 kilowatt. Any questions in this? Okay. The next question is a new high efficiency home heating system includes an air to air heat exchanger which uses energy from outside stale air to heat the fresh incoming air. If the outside ambient temperature is minus 10 degrees Celsius and the relative humidity is 50%, how much water will have to be added to the incoming air if it flows in a rate of 1 meter cube per second and must eventually be conditioned to 20 degrees Celsius and 45% relative humidity. So outside air is coming and you are exchanging heat with the inside air. So this is the heat exchanger if you see. The inside air is flowing on the red color portion and blue in the center portion there is outside air which is coming and it's exchanging heat. And they have given the outside air is at minus 10 degrees Celsius and 50% relative humidity, and you need inside air to be at temperature of 20 degrees Celsius and 45% relative humidity, and the flow rate is given as 1 meter cube per second. So we need to find out how much amount of water has to be added to bring to this temperature and relative humidity. So first we'll find out for the outside ambient air. So PV1 is your relative humidity into your saturation pressure. So corresponding to minus 10 is 0.2602 kilopascal. So relative humidity is 0.5. So 0.5 into 0.2602 gives you 0.1301 kilopascal. So this is your partial pressure of water vapor at state outside air. So now assuming your pressures inlet and exit is same, so 100 kilopascal, your dry air pressure is equals to 99.87 kilopascal. So using this we can find out the mass of air, dry air at outside air which is coming in. So your pressure into volume divided by RA into T. So your pressure is 99.87 and your volume flow rate is given as 1 meter cube per second, divided by 0.287 into 263.2. That is the temperature. So this gives you mass of dry air as 1.3224 kg per second. Then using this we can also find out specific humidity with the pressures which are calculated. So 0.622 into your partial pressure of water vapor divided by partial pressure of dry air. So 0.622 into both the pressures are known. So substituting that, we'll find out is equal to 0.0081 kg of water vapor divided by kg of dry air. Now this air is conditioned to 20 degrees Celsius and 45% relative humidity. So your at state 2 your water vapor pressure is again same relative humidity into saturated pressure at 20 degrees Celsius. So that is equals to 2.339 kilopascal, and your relative humidity is 45%. So that gives you your water vapor pressure is 1.0526 kilopascal, and using this we can calculate your specific humidity. So omega 2 is 0.622 into PV by PA. So PA can write it as 100 P minus PV. So that gives you your specific humidity as 0.00662 kg of water vapor per kg of dry air. So if you see your specific humidities are at state 2 is higher than state 1. So this says that you need to add some water to the air. So now if you do an mass balance across the heat exchanger, your mass of dry air will remain same. So mass of liquid which is coming in is equal to mass of dry air into your change in specific humidity. So mass of dry air which we have calculated is 1.3224 kg per second into your change in specific humidity. This will give you as 0.007683 kg per second or 27.66 kg per hour. So this is the amount of liquid which we have to put in the inside coming air to make it to bring it to temperature of relative humidity of 45% at 20 degrees Celsius. Any doubt in this?
No, sir, everything is okay, sir.
Okay. So next problem is a saturated air water vapor mixture at 20 degrees Celsius and 100 kilopascal is contained in a 5 meter cube closed tank in equilibrium with 1 kg of liquid air. The tank is heated to 80 degrees Celsius. Is there any liquid water in the final state? Find the heat transfer to the process. So you see, this is how there is a tank, and at the bottom you have 1 kg of water, and the rest of the tank contains a mixture of water vapor and air. So now you are adding in heat uh, to such that the tank contents is at 80 degrees Celsius. So now at this state, will there be any water left in the tank, or it will all evaporated and will be taken in by in the air? And also you have to find out what is the heat transfer happened during the process. So first, since your specific volume of water is very small, your volume occupied by the liquid will be very small. So if you see, your volume is nothing but mass of liquid present into your specific volume is the total volume. So that will give you 0.001 meter cube. So that is the amount of volume is occupied by the 1 kg of water. So the tank contains fully of air. So first, initially, this is at equilibrium. So if it's at equilibrium, that says that this is a saturated condition. So in the problem also it's given saturated air water vapor, which is at 20 degrees Celsius. So your water vapor pressure at state 1 will be equal to your saturated pressure corresponding to 20 degrees Celsius, which is 2.339 kilopascal, and your relative humidity is 1 or 100%. So now we can find out specific humidity using same relation between your pressures. So 0.622 into your PV by P minus PE. Your PV is 2.339, which we have found out, and your total pressure is 100 kilopascal. Substituting that, we can find out specific humidity as 0.0149. Now we know mass of liquid which is present. We can find out mass of dry air which is present. So mass of dry air is nothing but, using an ideal gas equation, PV by RT. So partial pressure of air is nothing but 100 minus your water vapor pressure. So 97.661 into your volume, which we have calculated, 5 minus 0.001, which is 4.999, divided by R into T. So R is 0.287 into temperature is 20, so 293.2. This gives you mass is 5.802 kg. So this is the amount of dry air which is present. So we know specific humidity and we know mass of dry air. So using that, we can find out mass of vapor which is present in air. So mass of vapor is nothing but specific humidity into mass of dry air. This gives you 0.086 kg. So next is at state 2. This whole content is at 80 degrees Celsius. So at 80 degrees Celsius, we'll see your what is the change in pressure of your dry air. So PA2 is 97.661 kilopascal into so this is a constant volume process. So P by T is PV by T is constant, because your volume is also changing from 4.999 to 5, because all the water vapor, assuming that all the water vapor is at evaporated. So 4.999 divided by 5. This gives you the pressure at state 2 as 117.623 kilopascal. So what is the maximum specific humidity which can happen at state 2? So maximum is your saturated pressure corresponding to 80 degrees Celsius. So W max is 0.622 into your vapor pressure, saturated vapor pressure corresponding to 80 degrees Celsius, which is 47.39, divided by your pressure of dry air, which is 107.623. So this gives you your W max as 0.2506. So W max is saying that your at saturation condition or 100% relative humidity, uh, the specific humidity corresponding to that is 0.2506. So if 1 kg of air water is going into air, and if it exceeds 0.2506, it says that it cannot take more than 0.2506. So there will be some amount of water which will be left. But if your specific humidity after evaporating 1 kg of water which was present in tank is less than 0.2506, then that says that the total amount is evaporated, and it can still take some more amount of water. But this being a closed tank, the water which you can add is 1 kg. So your actual uh, water water at state 2, water vapor at state 2 is initial water vapor which was present 0.086 plus 1 kg which you are adding, divide by the mass of dry air which is present, so 5.802. This gives you your W2 actual is 0.1872. So now this being less than 0.2506, this says that you can take even more amount of water vapor, sorry, even more amount of water. So there will be no liquid present at state 2. So now we know how much amount of water vapor is present, and the states, all states. So we can find out what is the amount of heat which we have supplied. So MA UA2 minus UA1. So this is the change in internal energy for the vapor, plus same for liquid. So at state 2, your MV2 UV2 minus MV1 UV1. So at state 2, your whole of water is at vapor state. So you are writing MV2 into UV2. At state 1, it is in two parts. Some part is in liquid form, 1 kg is in liquid form, the rest is 0.086 kg is vapor form. So MV1 UV1 minus M of liquid into U of liquid at state 1. So from steam table you can find out the internal energies, and for air you can write it as CV delta T. So CV is 0.717, and we know the temperature at end is 80 degrees Celsius and initial is 20 degrees Celsius, and we also know the mass of each of the components. So substituting that, we will find out the heat which has to be added is 2655 kilojoule. So this is the amount of heat which you have to be added to bring the whole content to 80 degrees Celsius. So moving on, the next question is air at 30 degrees Celsius and 1.05 bar and 80% relative humidity enters a dehumidifier operating at steady state. So moist air exits at 15 degrees Celsius, 1 bar and 95% relative humidity, and condensate exits in a separate stream at 15 degrees Celsius. A refrigerant flows through the cooling coil of the dehumidifier with an increase in its specific enthalpy of 100 kJ per kg of refrigerant flowing. Heat transfer between the humidifier and its surrounding and kinetic and potential energy effects can be ignored. Determine the refrigerant flow rate in kg per kg of dry air. So basically they have given there's a cooling coil. What happens is it is dehumidifying. It is removing some water vapor from the air. So initially the moist air is sent at 30 degrees Celsius and 80% relative humidity. When it passes through the cooling coil, some amount of water vapor condenses and it exits at 15 degrees Celsius, and the remaining air is coming out, and it has your temperature of 15 degrees Celsius and relative humidity of 95%. They are saying how much amount of refrigerant is flowing, how much amount of specific enthalpy change is happening in the refrigerant, and you need to find out what is the ratio of mass of refrigerant flowing divided by mass of kg of dry air. So we'll see how to solve this. So first, if you do an it's similar to a problem which we saw previously. So we'll do an mass balance. So mass of dry air will remain same throughout. So Ma1 equals Ma2 equals Ma. So but mass of water vapor will change. So at state 1, mass of water vapor 1 is equals to the mass of water which has condensed plus mass of water vapor which is present at state 2. So mv1 equals m dot v2 plus mass of water which has condensed. So dividing this by mass of dry air, so this gives me mass of water which has condensed divided by mass of dry air equals your change in specific humidity. So now if you apply an energy balance across the dehumidifier, so your Q is your mass of refrigerant which is coming. So mr m dot r hi minus he. So this is Q, cooling load which is present, plus mass of air which is coming in, enthalpy of air. So mass of air, dry air enthalpy plus mass of water vapor enthalpy, minus similarly for the exit air, minus the water which has condensed, enthalpy of the water which has condensed. So dividing this whole by mass of dry air and writing in terms of simplifying it to get m dot r by m dot a, we'll get your change in enthalpy of dry air between the states plus so omega 2 hg2 minus omega 1 hg1 plus omega 1 minus omega 2 into hf3. So hf3 is nothing but your liquid water which is coming out, enthalpy divided by hi minus he of refrigerant which is given. So now in this the dryer enthalpy can be found out using Cp delta T. So you know from the problem, you know the temperatures, and the enthalpies can be found out because your temperature is known. So correspondingly saturated vapor enthalpies and liquid enthalpies can be found out. The only unknown is the specific humidities. So for that we know the relative humidity at the inlet and exit. So from steam table we can find out the saturated temperature corresponding to 30 degrees Celsius and 50 degrees Celsius. So which will give me the vapor pressure corresponding to that. So PV is 5 into your saturated temperature saturated pressure at T1. So this gives you 0.03397 bar, and similarly at P2 is 0.0162 bar. So using omega is 0.622 into PV by T minus PV, this will give me specific humidity is 0.0208 kg of vapor by kg of dry air. Similarly at specific humidity at exit is 0.0102 kg of water vapor per kg of dry air. So now we know the specific humidities. On substituting the above equation, we'll find out that your mass of refrigerant required per mass of dry air is 0.418. So for 1 kg of dry air, and to make it 15 degrees Celsius and 95% relative humidity, the refrigerant required is 0.418 kgs. So that's what it says. So here there are only two application we did a mass balance, we did an energy balance. So using that, the only unknown which was required is the specific humidity, and we know how to calculate specific humidity, and we substituted that, and we can find out the mass of refrigerant by mass of air ratio. The next, I think this is my final problem. Problem is on cooling tower. So cooling water enters the condenser of a steam power plant at 30 degrees Celsius and leaves at 45 degrees Celsius with a mass flow rate of 3.75 into 10 power 7 kg per hour. So they have given the water which is going into a steam power plant. So it is going in at a 30 and it's coming out at 45 degrees Celsius, and the mass flow rate is given. Now this water is taken to a cooling tower where it is cooled before being returned. So ambient air at 25 degrees Celsius, 1 atmosphere and 45% relative humidity enters the cooling tower and leaves at 31 degrees Celsius as fully saturated. So makeup water at 25 degrees Celsius is also provided. Determine the mass flow rates of the dry air and makeup water. Neglect heat loss and fan power and assume that the pressure remain constant at 1 atmosphere. So we need to find out the mass flow rate of the dry air and of makeup water. So before going to the problem, I'll just give you the brief working of how the cooling tower works. So if you see, this is how a schematic of a cooling tower. So what basically in cooling tower is done is you are cooling the air by forcing air on the water. So for that you are spraying water at the top. So water is coming at state 1 and it's getting sprayed from a tower, so at a height, and from the bottom you are passing air. So this fan above, so this being an induction fan, you will push the uh, water air out. So when this air comes in contact with the water vapor, this will cool the water vapor, and it will take some amount of water from the water which is drip. So it will take some amount of water from the water, and the water vapor content in the air increases, and because of this the water will get cooled, because the water vapor which is going into the air has to convert from gas phase to vapor phase. So it will take away some latent heat, so that will cool the water. So and that water which is sprayed gets cooled and gets collected at down, and you can send it back to any processes. So because there is some amount of water which is lost in the process, you have to give some makeup water. So that's how a cooling tower works. So for this, now we'll see how to solve this. So we'll straight away take values from the psychrometric chart and the steam table. So H1 we know the water is at 45 degrees Celsius, so the corresponding enthalpy is 188.42 kilojoule per kg, and H2 is at 30 degrees Celsius, which is 125.67 kilojoule per kg. Third is your dry air entering. So mass of air which is entering is at 47 kilojoule per kg of dry air. So here the air entering is at 25 degrees Celsius and 45% relative humidity. So corresponding to these 2 points from the psychrometric chart, you can find out enthalpy as 47 and specific humidity as 0.009 kg of water vapor per kg of dry air. And at the exit they are saying that air is at 31 degrees Celsius and it is fully saturated. So fully saturated means your relative humidity is 100%, so it cannot take any more water vapor inside. So for corresponding to 31 degrees Celsius and 100% relative humidity, you will find out your enthalpy from psychrometric chart as 105 kilojoule per kg of dry air, and specific humidity as 0.029 kg of water vapor per kg of dry air. So you have to careful in psychrometric chart, it will be given in grams per kg of dry air. So we are dividing by 1000 to make it kg by kg. So you should be careful with the units there. And then H5 is the liquid of water, which is the makeup water which is given at 25 degrees Celsius. So that enthalpy is 104.75 kilojoule per kg. So when you do a mass balance across this cooling tower, so mass of water 1 plus makeup water minus mass of water 2 plus your vapor mass of water vapor at state 2 equals mass of water vapor at state 4. So since water which you are water which is coming in and going out is same, and the the change of water which is going in the air is being given by the makeup water. So m dot w5 is the makeup water is equals to the mass of water vapor present in the inlet minus exit. So this gives me mass of makeup water is equals to mass of dry air into omega 4, which is the specific humidity at exit, minus specific humidity at inlet of the air. So m dot a into omega 4 minus omega 3. So omega 4 we know the air which is coming at exit 100% relative humidity is 0.029, and at the inlet air specific humidity is 0.009. So we know a relation to find out makeup water. So when we apply an energy balance, so Q is 0 and W is 0 because we are not supplying any heat or any work in the cooling tower. So mass of air which is coming in minus H3 minus H4 minus exit, plus mass of water which is coming in, plus mass of makeup water which is coming in, minus mass of water which is going out. So using this we can find out the mass of air. So we have relation for makeup water and mass of air. So substituting that and all the enthalpy values, we can find out mass of air, because mass of inlet water is given as 3.75 into 10 power 7 kg per hour. So using this and substituting all the enthalpy values, we can find out that mass of dry air which is required is 4.21 into 10 power 7 kg per hour. And using the previous expression for makeup water, substituting, we will find out that the makeup water which is required is 8.42 into 10 power 5 kg per hour. So you see the mass of water which is cooled is 3.75 into 10 power 7, and during the process you have lost 8.42 into 10 power 5 kg per hour of water is taken away by the air in the process of cooling it from 45 to 30 degrees Celsius. So any doubt in this? I think I finished what I prepared. If you have any doubts, you can ask. So these are from multiple books, so you can find it in somewhere on the behind Moran Shapiro and some other books which are it's all I took 3-4 books, so it's from all that. Maybe I'll add a reference slide of where I am putting. I'll put a extra this thing, you can refer to it. Some many problems are from I think Moran Shapiro. You can see at the end unsolved problems, so you can see from there. You can get some more problems from there. Any other doubts? It's the reference book which is mentioned in the course. I'll anyway add a reference slide where I have taken this problem in the folder where I am uploading the videos. If you have any doubts, we can ask, or else we can end the session today.
Okay, sir.
Okay. Okay. Thank you.
Okay, thank you, sir. We will wait for the next class. No problem.
Okay.
Everything is very clear and it is very vivid to us.
Okay. Thank you. Thank you. If you
Okay.
have any doubts, you can ask even in next class. It's okay.
Sure, sir. Sure, sir. Thanks a lot, sir.
Thanks. Okay. Thank you for joining. We'll see you in next class.
Okay, sir. We're leaving.